This is 6.1.2. In this figure, we'll study and examine the different types of Fourier transform. Here, I'll show you actually there are 5 different types of Fourier transform. There are the continuous time Fourier transform, and there are 3 discrete time Fourier transform. Continuous time Fourier transform can be operated on periodic signal as well as aperiodic signal. CTFS is continuous time Fourier series. CTFT is continuous time Fourier transform. Both these approaches can be used to deal with continuous time signal. However, only CTFT can be used to deal with aperiodic signal. Similarly, if the signal is discrete time, we'll use discrete time Fourier series, discrete time Fourier transform on periodic signal. So this is the signal. The x-axis is time in sample, and the y-axis are the values. This is a periodic sequence. Remember, both DTFS and DTFT can be used to analyze periodic signal. For aperiodic signal or not periodic signal, only DTFT can be used, discrete time Fourier transform. Now, you'll be wondering, if we already covered this periodic and aperiodic for discrete time, why is there something else? And this something else is called DFT. DFT is actually DTFS. DFT is actually DTFS used to analyze a sample sequence, n sample sequence of xn, and ignoring the sample outside the window. I'll give you an example. Here, we're using DFT to analyze this 5 sample signal. This 5 sample is like the same as this 5 signal. 3 on and 2 off. What is outside? It's not periodic. It is not like here we have a sampled signal that repeats itself every 5 samples. Here the samples don't repeat. When we take this and use DFT on this, we are pretending actually that it is periodic. Later on, you'll realize that there are some things that you have to take care of when you are using DFT. So this is the nice picture to show the 5 Fourier transform pairs, or the 5 Fourier transform approaches. The next page shows you the equations associated with the analysis as well as the synthesis. So here's analysis, here's synthesis. What does analysis means? Analysis basically takes our signal, and here I only will draw you the DTFS, DTFT, and DFT. Takes the original sequence x of n and breaks it down into complex exponential. So when we say we take the DTFS of this signal, we're asking you to calculate CK. If we ask you to calculate the DTFT of the periodic signal, what you have to do is to calculate the DTFS and then convert it into the DTFT representation. We'll show you how later. The really trick is that you can see the XCK, which is the signal, which is the representation in the frequency for DTFS, is reused in DTFT. Here the CK. Right, what about DTFT itself? The direct equation to use DTFT is to perform a summation from -infinity to infinity of all time of the signal x of n. And you will realize that if you try to apply this on periodic signal, then we'll never find it to converge. And that is why when we find x of omega for periodic signal, we have to use CK to help us. CK can be calculated because we are only using one period of the signal. So this is x of n for one period, and this is the equation to find CK only across one period, and therefore this value will exist. You realize that DTFT, because the sequence is aperiodic, will stretches from all infinite time. This summation might not exist. This summation exists when, in this example, it shows you that only 3 samples is non-zero, the rest are all 0. Okay, so when you have finite support. Lastly, in the DFT, this equation is used to calculate the coefficients of the frequency representation of x of n. Look at this equation carefully. This part is the same as DTFS. Summation of n equals to 0 to n minus 1, summation of n equals to 0 to n minus 1, x of n, then e to the power minus j 2 pi over n kn. These two are the same. The only difference is 1 over n is being used to normalize for ck. There's no 1 over n here. Now you'll be wondering, where's the 1 over n then? And the answer is that in DTFT, strangely enough, it is at the synthesis equation, which takes the frequency representation and converts it back to x of n. While in the synthesis equation of DTFS, there's no 1 over n. Now, this will cause many students many grief. You'll realize that DTFS formulation and DFT formulations are not, well, DFT's formulation is very standard, but not DTFS formulation. This 1 over n becomes 1 over root n, 1 over root n, and so on and so forth in different books. But the take-home message, at least to this point, is that all these equations are for analysis and synthesis, and in this one page you can see all 6 of them in the single page. Lastly, this equation is the synthesis equation for DTFT. Remember, x of omega, capital Omega, is the DTFT representation. X of omega is continuous. That's why we use the integration. Integrate x of omega times e plus j omega n to reconstruct x of n. Okay, so in this chapter 6, we are only interested in all these 6 equations and their use cases. Thank you.